So in chapter 2, we're going to start talking about atoms and molecules, which you'll recall are the first two steps in the hierarchy of organization of biology. And these are really the chemical foundations of life. In other words, the atom is the basic unit of chemistry, but it's part of what makes up a cell, which you'll remember is the basic unit of life, of biology. So we have to start with the chemistry first. And so we're working our way up this hierarchy of biological organization, starting from the beginning. All right, so your study objectives, again, these are good for your review after the lecture is done. The terminology is quite massive in this chapter. If you've had chemistry in the past, then some of these words will already be something that you can refresh pretty easily, and then there probably will be some new ones that you'll be adding. If you've never had chemistry, then the terminology is quite a bit, and I recognize that. And so that's a lot of the work is in the terminology and learning the terminology. All right, but let's start with the atom. So the atomic, meaning of the atom, the atomic structure. What is the structure of an atom? So atoms consist of smaller particles that are sometimes called subatomic particles, S-U-B-A-T-O-M-I-C, subatomic, meaning smaller than the atom itself. But an atom is made up of smaller particles called protons, neutrons, and electrons. And in fact, I don't want to blow your mind, but these particles actually contain smaller things as well. And the components within a proton, a neutron, or electron, that study is what we call quantum mechanics. So it blows my mind, and we're certainly not going to try to talk about what makes up a proton, for example, or what makes up an electron. But so we're going to say that the smallest particles that we're going to concern ourselves with are protons, neutrons, and electrons. So in an atom, if the atom doesn't have an electrical charge, we call it neutral. So a neutral uncharged atom always has, this is a rule, the number of protons in that atom will always equal the number of electrons. And that's because if you look up top, protons are positively charged particles and electrons are negatively charged particles. So each proton has a charge of +1. Each electron has a charge of -1. And we're talking about electrical charges, so positive and negative electrical charges. And the protons, though, are located in what we call the nucleus of the atom. And that's different than the nucleus of a cell. The nucleus of the atom, atoms are very small and they have in the center portion, we call that the nucleus. So the protons are found in the nucleus, the neutrons are found in the nucleus. There's nothing, well, for our purposes, you can think of the protons and the neutrons just kind of mashed together in this middle. And then the electrons are moving around the nucleus at some fixed distance, some distance. And we call that area that they're moving in the orbital around the nucleus. Sometimes it's called the electron cloud, but we're gonna stick with the term orbital and just kind of keep things simple, since when you take chemistry, you'll get some more of that language. But we're just gonna think of this as this zone where the electrons are moving around. Now they don't really go much beyond their orbital, but they move. And so at any one time, if you took like a snapshot picture, you might have the electrons over here, and then another time the electrons might be on the other side. So they move around constantly. So, but the protons and the neutrons are in the center. So in a neutral atom, the number of protons would equal the number of electrons. Now the number of protons in an atom is called the atomic number, which doesn't sound like a very specific term, but it actually is. The atomic number specifically means the number of protons in that atom. And the number of protons in the atom is what determines the identity of the atom. The number of neutrons does not determine the identity of the atom. The number of electrons does not determine the identity of the atom. The rule is the number of protons tells you what the identity of the atom is, or what kind of atom it is. So for example, carbon, the symbol for carbon is C. And carbon has 6 protons. And so the 6 that's in this symbol here is the number of protons. So any atom that has 6 protons is carbon, because the number of protons determines the identity, the type, the name of that atom. So it's carbon. All right. But there can be different numbers of neutrons or electrons in an atom of carbon, but it would still be carbon. Okay, so carbon has an atomic number of 6. Okay, and the number down here below indicates the mass of the atom. So let's say you have an atom of carbon. It has 6 protons, and the total mass of the atom is 12. So each proton has a mass of 1, and each neutron has a mass of 1. So if the total mass of the atom is 12, which is the larger number, and if the number of protons must be 6, then on the case of this atom, there must be 6 neutrons, because that's 6 neutrons each weighing, each having a mass of 1, and 6 protons each having a mass of 1. It gives you a total mass of 12. But you could also have a carbon that has 6 protons. All carbon has 6 protons, but it has a mass of 13. In that case, that atom of carbon would have 7 neutrons. So there's typically slightly different versions of every atom that are possible. And the different versions that have different numbers of neutrons, we call those isotopes. All right. So isotopes is defined, isotopes are atoms of a single element, for example, carbon, that possess different numbers of neutrons, and that means the mass number is different. All right. So carbon 12, 6 protons, carbon 13, 6 protons, carbon 14, 6 protons. But this number here indicates the total mass, so you can subtract and figure out that carbon 12 has to have 6 neutrons, carbon 13 would have to contain 7 neutrons, and carbon 14 would have to have 8 neutrons. Interestingly, electrons don't have a significant mass, so we don't add that. The mass of the electrons is what we call negligible. All right. Some isotopes, because they have so many neutrons, it makes the atom unstable and it can actually break apart, and we call those radioactive isotopes. So radioactivity is actually refers to atoms that are breaking apart. And radioactive isotopes cause damage to your cells, especially your DNA. But we're not going to talk too much about radioactive isotopes. Let's focus on just general, any kind of isotope. So some isotopes are stable. Carbon 14, carbon 13, carbon 12, fairly stable. But they just vary the number of neutrons, which means carbon 14 weighs more. One atom of carbon 14 weighs more than one atom of carbon 12, but they're all carbon. So this is a nice little simulation, and I'll put the link up for you, or if you can't find it, you can go and click on this link here, and you can play around with the concept of isotopes. So in chemistry, you would learn about what we call the periodic table, and here's a really miniature version here I was able to fit on the slide. The periodic table is a chart of all of the elements, and it indicates how many protons each element has in each atom. So hydrogen, it's really small, but I think you can see hydrogen has 1 proton. So the atomic number of hydrogen is 1, and the symbol for hydrogen is H. And then over here, you kind of read the chart across on the rows. The next one is helium. Helium has an atomic number of 2, and its symbol is He. Then you go to the next row. Lithium, Li, has an atomic number of 3, so 3 protons, and so on and so forth. All right. Now, we said that for neutral atoms, uncharged atoms, the number of protons, which is this atomic number, also tells you how many electrons that atom would have. And so if you have 1 positively charged proton, you would have 1 negatively charged electron. Those charges cancel out, and we say that the whole atom is neutral or uncharged overall. If you had helium, has 2 protons, it has 2 electrons, it's neutral. Lithium has 3 protons and therefore 3 electrons, so electrically neutral. One thing that the periodic table displays, it displays the elements in columns. I hate it when it does that. Columns up and down, according to how many valence electrons would be in the atoms. And valence means the number of electrons in the outermost energy level, or the outermost orbital. All right. Typically we think, the simplest way to think of an atom is usually called the Bohr model. The Bohr model, which I'll show you on the next slide, it kind of thinks about an atom in the sense of like the orbitals are like circles, concentric circles around the nucleus. So the electrons move in a circle around the nucleus, like kind of like the planets go around the sun. That's not actually accurate, but it's good enough for us to be able to figure out some basic things that we need. And so it's almost the way I always think about it. Just in order to solve a problem, you can think about the atom in what we call the Bohr model. When you take chemistry, they'll crank it up a little bit and it'll get a little more complicated than that. But we can do it in a very simple way for our purposes. The rule for the orbitals is this. You have a nucleus in the center, okay? Then you have an orbital where these electrons that move around at a certain distance from that nucleus, which is the red dot. Then you have another orbital that's a little further away but in a circle. Then you have another orbital that's even further away but in a circle. Sorry about that. And so it's like circles around, you know, where the nucleus of the atom is like equivalent to the sun of the solar system, if you want to think of that analogy. And so in the way the orbitals work is the orbital that's closest to the nucleus can only hold a maximum of 2 electrons. And then the next orbital can hold by itself 8, and the third orbital can hold by itself 8. And then there are more, but in biology, you're going to see that the chemistry of biology, at least at the introductory level, is pretty simple, pretty straightforward. So we're going to think about one nucleus with 3 orbitals and kind of thinking about it in the way I've drawn it here. If you have an atom that has, let's say, 8 electrons, so that would be that would be oxygen. So oxygen contains 8 electrons. You can't really read it here, but oxygen has an atomic number of 8 protons, and therefore 8 electrons. The electrons will be distributed in the orbitals, first distributed in the orbital closest to the nucleus, and then when that orbital is full, then the rest of the electrons will be in the next orbital, and if that one gets full, then they are out in the third. So if you had 8 electrons in oxygen, you would have 8 protons in the nucleus, all right? Then you would have the electrons. There would be 2 electrons in the first orbital. The first orbital can only hold 2, or what we call the first shell, or the first energy level. Those are all terms that we would use. The second can hold up to 8. So we said there's 8 total. So for the first 2 are in the first energy level, and then the rest of the 6 would be in the second energy level. Now we said that the second energy level can hold up to 8. So the second energy level is not full in this example of oxygen. And so that means that oxygen has 2 energy levels, because any energy level that doesn't have any electrons in it disappears. So the third energy level would just disappear. So in the oxygen example, the first energy shell, the first is full with 2 electrons, and the second energy shell is not full because it has the other 6. And so the outermost shell that still has electrons in it is called the valence shell, the valence level. And so in the case of oxygen, the second energy level is the valence level, and it would contain 6 electrons. What atoms are trying to do, if you want to give them like some kind of intent, what atoms are trying to do is to become stable. And the best way they can become stable is to have a full valence shell. So if you have just the first energy level only, then it needs to have 2 electrons to be full. If you have the first level and the second level, then you need to have 2 in the first level and 8 in the second level to be full. And so either of those examples would be, those atoms would be stable. If you have 3 energy levels, like the picture I drew here, you would have to have 2 in the first level, 8 in the second level, and 8 in the third. And that atom would be stable. So every atom is trying to achieve stability, which you can kind of understand, right? I mean, stability is a nice thing to have. And so think about it, think about the atom trying to achieve stability. Now, the octet rule is that atoms are trying to completely fill their outer shell. Octet refers to 8. The first energy level, though, only really has 2. But the second and the third those shells can hold up to 8. And so in order to be stable or inert or non-reactive, there must be a full energy shell, okay? And so all atoms are in some way, you can think about it as they're trying to reach that goal, although some of them probably will never be able to reach it, but they're going to behave in a way that makes sense in terms of them attempting to reach stability. All right. So here's the Bohr model. And this is hydrogen. Hydrogen has an H for a symbol. Hydrogen actually only contains 1 proton, no neutrons, and 1 electron. So in reality, a hydrogen is just a proton in the nucleus and 1 electron in the first shell. So it's a very simple model. All right. Let me get rid of that eraser. Okay, so this picture, but they do show you the second and the third shell just to show you, but those would disappear because they don't have any electrons in them. So you can think of hydrogen as only having the first shell, all right? And so that's the Bohr model of hydrogen, okay? Electrons that are in the first shell have less energy than electrons that are in the second shell, and electrons in the second shell have less energy than electrons in the third shell. The third shell has more energy. All right. So this would be the Bohr model of a couple of examples. Hydrogen only has 1 electron, so we're showing that here. I want to get my pointer back. Helium has 2 protons and therefore 2 electrons. So helium has a full first shell. The first level is full. So helium is stable. Lithium has 3 electrons, so 2 in the first shell, 1 in the second shell. And what you can see is, all the way across these examples anyway, neon has 10 electrons, 2 in the first shell, 8 in the second shell, so neon is stable. But fluorine is not stable because it has 2 in the first shell, but it only has 7 in the second shell. So it would need to get 1 more in order to fill its second shell and be stable. So the way fluorine is going to behave in the world is in some way to try to get 1 more electron. So fluorine is out to get another electron. That's its goal. if you want to think about it that way. Fluorine doesn't have a brain, but if it did, it would be thinking, I need to get another electron. All right. And you keep going, and the third level you have, for example, sodium, which is Na, 2 electrons in the first shell, 8 electrons spread around the second shell, and then 1 electron in the third shell. So if you add those all up, that's 11. So the number of electrons is 11. All right, so you can see how these are set up in the Bohr model. All right, you won't have to draw a Bohr model, but I think it's helpful that you can think through how the electrons would be distributed. The first 2 would be in the first level, the next 8 in the second level, and if there's even more, then the next 8 in the third level. But most atoms don't have a full valence shell. Only the ones in this picture on the far right. So on this picture, only these atoms have a full valence shell on their own. So these guys never want to react with anyone because they're already stable. The rest of them are looking to either gain or lose electrons in order to become stable. Okay, the rest of these that I didn't circle. So you can think of it, that's the rules for how they're going to react. All right. Now, the way the real orbitals are shaped, if you've had chemistry, you probably remember the s orbital is spherical, and then the p orbitals are shaped like, we usually say dumbbells or like a figure 8 or something, Q-tip or something like that. These are the real shapes of the orbitals. They're actually not the way, the Bohr model kind of puts them in these concentric circles. I don't care that you know what the real shapes of the orbitals are, except I don't want you to get to chemistry and be totally shocked when they kind of tell you the truth about how the electrons move at these different levels. So for us, it's not important, but for chemistry, it becomes pretty important. So I'm just flashing this in front of you to show you that the real shapes of the orbitals is not just circles. All right, but we're fine to leave it at that. Now, in biology, in biochemistry, there's really only 12 elements on that whole chart of the periodic table. There's really only 12 of those that are really important, that you would encounter often in your study of biology. And of those 12, really only 4 are really important. So the 4 most important elements that we need to study if we're starting our study of biology and biochemistry is carbon, hydrogen, oxygen, and nitrogen. You need to memorize those. All right, just memorize that these are the 4. Carbon, hydrogen, oxygen, nitrogen. There are some other elements, we call them trace elements because you don't need very much of them, but we're going to start with these 4, carbon, hydrogen, oxygen, nitrogen. All right. All right, more terminology. I'll let you study that on your own. Okay, actually, let me go back. Let's look at the Bohr structure of these 4. All right, carbon has in its valence shell, and that's really what matters. Carbon has in its valence shell, sorry about my dog barking, it has 4 electrons in its valence shell, and it wants 8, but it has 4. Hydrogen only has 1 electron, so it only has 1 electron in its valence shell, which is the first level. All right. Oxygen has 6 electrons in its valence shell, so it's hoping to find 2 more. And nitrogen has 5 electrons in its valence shell. Okay. So this is going to become important, all right, because it's going to predict how many other atoms that each of these atoms will try to interact with. And so it's going to set up some rules for us, because remember, each atom is trying to get a full valence shell. So each interaction that an atom makes is called a bond. And so carbon has 4 electrons in its valence shell, and if it can interact with 4 other atoms in some way, it can sort of fill its valence shell. So carbon is going to want to make 4 bonds. Hydrogen is going to try its it only needs to make one bond to fill its valence shell. Oxygen needs to make 2, and nitrogen needs to make 3. So each bond that the atom makes with another atom is going to add something. It's going to add the equivalent of an electron to its shell. We'll see how that works in a minute. All right. So what are bonds? Bonds are it's really a force between atoms that hold them together. All right. And there's fundamentally 2 kinds of bonds that are really important within a molecule. And by within, I mean directly between the atoms that makes up one molecule. So within one molecule, a single molecule, you will tend to have either ionic, it's hard to write with my mouse, you will either have ionic bonds that hold that molecule together, or you'll have covalent bonds that hold that molecule together. Covalent bonds are stronger. In fact, covalent bonds are the strongest bond of all. Those hold the atoms to each other in one molecule. Now, hydrogen bonds and van der Waals forces, those tend to hold together one molecule to another molecule. So this hydrogen bonds and van der Waals forces, we usually say, typically are bonds between multiple separate molecules, usually. So let's start with the ionic and the covalent, because that's really where we need to be. Hydrogen bonds will be important later. Van der Waals, we're not really going to talk about van der Waals too much. So if you just want to kind of ignore that one for the purpose of our course, that would be okay with me. Okay, you may see it later in chemistry class. So let's start with ionic. Ionic bonds hold atoms together to make a molecule, and then covalent bonds hold atoms together to make a molecule. An ionic bond is just a bond between 2 ions. And an ion is just the name for an atom that does have a charge. All right, a charged atom. So we said that if an atom had, 5 protons, and then it would have 5 electrons, then it would be neutral. But what if it doesn't have the same number of protons as it has electrons? Then it would have a charge. If it has more electrons than protons, then it would have more negative charges than positive charges. And so it would be a little bit more negative. If it has more protons than it has electrons, it would have a little more of the positive. Because remember, protons are positively charged. So we have names for these. The term here is cation. It's almost like cat, like meow. A cation has more protons than electrons, so more positive charges than negative in that atom, and therefore the atom takes on a positive charge. It's not neutral. An anion has a negative charge, and the way students tell me that they remember it is the cation has like the T, they think of that as like a plus, so that's the positive ion, and then the anion has the N for negative. I don't know if that helps. The cation has the T, which is the plus symbol for them, and the anion has an N, has 2 N's really, and that N stands for negative. So just some mental tricks. No matter how you get a cation and an anion, if they come close to each other, they will be attracted by an electrical charge. So in this picture, you have sodium ion, and you have a chloride ion. Sodium has a positive charge, chloride has a negative charge, and so by opposite electrical charges, they will attract. It's magnetic. It's a magnetic attraction in the literal sense, because opposites attract, right? In electricity, in opposites. Okay, so Now, the way ions form, there can be different ways. This picture is trying to show you one way that ions might form. Because remember, chlorine wants an extra electron. It wants to fill up its valence shell. And sodium wants to give away the one electron it has in its valence shell. Because if it gives it away, then that valence shell disappears, and then it goes to the previous valence shell, which was full. So that's just showing you a way that the ions might form. But once they form, no matter how they form, any two ions that are opposite in charge will tend to form a bond if the two ions come close enough together in space. Now, covalent bonds are much stronger. Ionic bonds are I would call them medium strength. Covalent bonds are very strong. Covalent bonds are not the attraction of oppositely charged atoms or oppositely charged ions. Covalent bonds is defined as the sharing of electrons. All right? The goal of making a covalent bond is for the atom to try to satisfy the octet rule, to try to have 8 in its valence shell. I usually think of a covalent bond as living in a fantasy world. Each of the atoms is going to live in a fantasy world. Okay, stick with me here. Let's say here's hydrogen in this picture. Hydrogen has one valence electron, it wants one more. And it's going to behave in a way to try to get one more. Here's another hydrogen down here. Same thing, it wants one more and it's going to try to get one more. Oxygen has 6 valence electrons and it wants 2 more. And what the atoms will find is that if the hydrogen comes close enough together to the oxygen, and this hydrogen comes close enough together to the oxygen, then what will happen is the nucleus, well, it's not a person, but I kind of put some human characteristics into this. I think, okay, the hydrogen is looking around and it's saying, okay, how many electrons do I have? 1, 2. Oh, I'm stable. The hydrogen here sees the same thing. How many electrons do I have? 1, 2. Now really, guys, this is a fantasy world, right? Because you can see as well as I can that the hydrogen only really has the one white electron and the red one is really coming from the oxygen. But the hydrogen doesn't care. He's willing to live in any fantasy world. As long as he stays right here, this close to the oxygen, he can pretend like one of those oxygen electrons belongs to him. And as long as this hydrogen stays close enough to the oxygen, he can pretend that one of those electrons from the oxygen belongs to him. So each of them is looking and saying, oh, I have 2. I must be stable. The same thing with the oxygen. The oxygen is looking and saying, I have 8. But really, we can all see that really he still only has 6, and he's kind of picking up one white from each of these hydrogens. But he lives in this fantasy world where he thinks he has 8. And so all of them are benefiting from living in this fantasy. So as long as they stay in this position near to each other, they can all maintain this fantasy and they will not let go of this fantasy. Or in chemical terms, the stability of it is so important that they will not move apart from each other. Okay? This makes them stable, and the goal of any atom is to be stable. So by being close to each other in this position, they are stable. And so this is called sharing of electrons, as we call it, sharing. The oxygen is sharing its electrons with the hydrogen is sharing its electrons with the oxygen, and everybody feels like they have a full valence shell, but in fact, in some ways, I mean, they don't really each have a full valence shell. But that doesn't matter. That will create a bond that will hold these atoms together in this way. And so when we draw molecules, you can draw the Bohr structure here, but that starts to get very cumbersome. And so we start drawing it like this little picture here. We just put the symbol for the element. Hydrogen is H, oxygen is O, and then a straight line indicates 2 electrons. So you can see that there are 2 electrons being shared here and 2 electrons being shared here. So this line represents 2 electrons and this line represents 2. And then the other electrons for oxygen we don't necessarily need to draw. You may see them in some books drawn, but But a bond is a straight line, and that indicates a covalent bond, not an ionic bond. All right, so covalent bond is a straight line. It's very strong, and it indicates where each atom that's connected by that line is sharing one electron with the other, such that 2 electrons total are being shared in that bond. All right, I'm going to take a break, and we'll come back in the next section and talk about electronegativity.